Okay. So here we go. The yeah, page one. Is that shocking to you? So the first thing is net force. This box over here kind of demonstrates net force. You'll see the word net a lot. We'll have net force. We'll have net work.
Fishing net.
Net. No, not fishing net, but various. What? Net work. Like the net amount of work that's done. And what whenever you see net, at least in physics, that means it's a vector sum. And vector just means taking into account directions. So if I want to find the net force on this block, I don't just add up 2 plus 2 plus 5 plus 3. I account for all the directions. So does anybody know what would the net force acting on this block be? It's a vector, so we need to give direction and magnitude. Ben Hood? 2 newtons to the right. 2 newtons to the right. We'll go ahead and write that. 2 newtons rightward. Or plus 2 newtons. That'd be another way to write it numerically. So net force is the vector sum of all the forces acting on an object. And the symbol that I'll use, a lot of people just write F and then sub NET for F for net force. I like to use the summation symbol, so I write net force that way. That's my symbol for it. Let's see. I want to name a couple of these forces. So this, if this were a block just sitting on my desk, or it could be the mouse right now, what's the net force acting on my mouse?
Gravity.
Well, is gravity acting on my mouse? Yes. So if I were to draw this, I'd have an arrow like this. I don't know what the weight of my mouse is exactly in newtons, but I would have the force of gravity pushing it down. Is that the only force acting on my mouse?
There's force going to the sides.
Like if, well, yeah, the desk. So when it's on my hand, gravity's pushing this down, but if there were only the force of gravity, it would be in free fall. That's what free fall is. So there's got to be something pushing the other way, and that's my hand. And yeah, there is air pressure. If I want to try to save face for Darian, there is air pressure pushing from every direction on here too, even upward from the bottom. There's air pressure pushing all around. So what am I getting at? Oh, the name of this force. So this force, let's just call this the weight. We'll come back to weight in a little while. And then this force is the normal force, which I feel like is an unfortunate name for a force. But it's called the normal force, and sometimes, well, usually I'll just write F sub n for it. And normal, in most people's language, means ordinary, but in sort of physicsy geometry talk, normal can mean perpendicular. So the normal force is a force exerted by a surface, like the surface of my desk is exerting a normal force on the paper. My paper is exerting a normal force on the mouse. It's the force exerted by a surface perpendicularly to the surface against something that is sitting on the surface. So here's what I'm going to write. The force exerted perpendicularly outward by a surface. And it may seem like kind of a stupid force to talk about right now, and I agree with you. At this point, it's kind of, I don't know. There's not going to seem like there's a lot of point in it. But later on, the normal force is going to be really useful. We're going to be talking about the normal force a lot. I just want to get it out there now. Okay, Newton's first law. You've probably heard this one before. Objects in motion remain in motion in a straight line at a constant speed, and objects at rest stay at rest. That's sort of that's what's happening, unless they're acted on by an outside force or an unbalanced force. There's a much more succinct way to write this. In fact, this whole first part, I can write this in 4 words. I can describe what's going on here. So see if you can think of 4 words that describe a situation where objects in motion are remaining in motion in a straight line at a constant speed, and objects at rest are staying at rest. What's a much faster way to say that? Stay in motion, but they don't change direction and they don't change speed. That we've got to convey that too.
You gotta push.
Objects move when pushed.
Objects remain, I don't know, constant, I don't know.
This is all describing one characteristic. If you think back to kinematics, this describes in that list of things that I would make V0, V, A, delta T, or delta X, delta T. This is really just telling us about one of these in particular.
Velocity without acceleration.
So velocity remains the same. Right. So if velocity is constant, what's a shorter way of saying constant velocity? 0 acceleration. So all this is really just 0 acceleration.
You said 4 words.
Yes. My 4 words are objects have 0 acceleration.
That's 5. Wait, never mind.
I had to count again. It's okay. I carefully counted, but that doesn't mean I miscounted. I didn't miscount. So objects
Acceleration is really long.
have, yes, it's at least 2 words long. 0. Oh, I'm writing it in the wrong place. I'm going to write it down here by the simpler version. Objects have 0 acceleration. That takes care of all those cases they were talking about there. If something's moving in a straight line at a constant speed, it has 0 acceleration. If it's at rest and it's staying at rest, it has 0 acceleration. This just really fleshes out all the different ways you can have 0 acceleration. And then there's, what's that?
And then is it just unless they accelerate?
Well, duh, yeah, objects have 0 acceleration unless they accelerate.
Maybe 6
But
words and be objects have 0 acceleration by themselves.
have 0 what?
Like
By themselves. Yeah. So this next part though, that would be more succinct. But I'm going to throw in this new definition or new word that's up here. So I'm going to not really shorten the rest so much. Objects have 0 acceleration unless they experience a net force. So my mouse would be demonstrating this right now. It's an object with 0 acceleration, and it's not experiencing a net force. Now, if I wanted to accelerate it to the left, what could I do?
Push it.
I can start to push it. And now that when I start to push it, there's a net force, and it's the force is leftward. But actually, as soon as I push it, there are 2 more forces acting on this. Does anybody know what the 2 forces are that just came into existence? Yeah, there's the force of my hand pushing it to the left, but there's a force of friction pushing it back to the right that's opposing me. So there are 2 forces that are new. But the net force is left. At least when it started to move, it was. Oh, if I push it at a constant speed, what's the net force now? What's the acceleration if I push it at a constant speed?
0.
0. So this if I really did push it at a constant speed in a straight line, it would have 0 acceleration and there would be 0 net force. Oops.
Yeah, you're clicking.
Oh, there. Yeah, I'm pushing the mouse in strange ways. So if I push exactly as hard as friction's pushing against me, they'll balance out and there'll be 0 net force, so there's no acceleration. Okay. This is just asking us to say, what could something be doing if there's no net force acting on it? So imagine my mouse. There's no net force acting on it. What are 2 possibilities for things it could be doing?
Moving or staying still?
Well, it could be staying still, but just saying moving would not be enough.
Consistently moving.
Yeah, so moving with a constant velocity. So you could, you have to have a constant velocity. You have to have zero acceleration. So you can have zero constant velocity, or you can be moving with constant velocity. But one way or another, velocity's got to be zero, or got to be constant. Constant, zero, zero velocity. And here's a trickier one. So when there's no net force, these are the two possibilities for something. And when there is a net force, let's say the net force on, this thing is 5 newtons. What could it be doing?
Anything.
It couldn't be sitting still, and it couldn't be moving with a constant velocity.
It could for a second.
So Celine, what were you going to say?
Anything but random.
Describe 3 different kinds of motion where they're different. They're fundamentally different, and none of them is staying motionless, and none of them is moving with a constant velocity. What are some other ways to move? Basically, with acceleration. What are some ways you can accelerate? There are 3 ways I can think of. They're very simple. So I can speed up. I can slow down. The third one is trickier. So you can have something that's staying the same speed, but it's still accelerating. How? Haven't talked about this in a while. Acceleration's a vector. That's a hint. Vectors have speed and direction. So how can you be accelerating without speeding up and without slowing down? Changing direction. So changing direction. And so if something is going around a track, I mentioned this before, if you've got a car going around a track at 60 miles per hour constantly, never varying from 60 miles per hour, it's still accelerating because its direction here is that way and its direction down here is that way. So its velocity is changing. And you can have this speeding up and changing direction. You can have slowing down and changing direction at the same time. Okay, now to this. This feels like I put too much space in here. I don't know why I have this much space on this sheet. I feel like I could have made it 26 pages. That would have been better. So Newton's first law is called the law of inertia. And inertia is just resistance to acceleration. And so some things, if you want to accelerate them, they're easy to accelerate. Other things are hard to accelerate, either meaning they're hard to speed up or they're hard to slow down. What kinds of things have the most inertia? Heavy things. Is that always true? I can think of a thing that weighs nothing and has a lot of inertia. Heavy things is true. If we went through this,
like a feather or something.
it would be light.
Yeah.
So
It's not like it's not like speeding up really fast or accelerating, I guess.
so you're thinking air resistance is sort of slowing it down, right?
Yeah.
Right. But if I tried to, if I just grabbed the feather and I tried to push it down like this, that would be pretty easy.
Oh yeah.
So I'm actually being kind of a smarty pants, and I'm thinking of, let's say we had well, first let's write the answer. The things with the most inertia are the most massive things.
Oh, so like a steamship.
Like a steamship, exactly, yes. Steamship, a train, yes. That's the archetypal massive thing.
Things that are more massive have less ability to move.
Right, you can't change direction. You just keep going straight. Exactly.
It's like right of way. It's like
So the steamship gets the right of way. The
Seems so obvious.
SS something, you're swimming along and then here comes the SS, this or that. That happens all the time.
it's because like big steamships always have the right of way because they can't move.
Dude, literally where?
No, but why does that come straight to your mind? Why did a steamship come straight to your mind?
Because they're massive. Have you ever seen a steamship?
Yes.
huge.
But things with engines don't have. But things with engines don't have a lot.
Yeah, and they don't have the panache. They just don't. They're not
Like you're
cool
sailing,
like steamships.
get out of the way.
So, but I specifically wrote massive, not heavy.
I'm gonna get off your smarty pants thing.
Yeah.
Are you saying that you could just be in space?
Right.
Yeah.
So if you just imagine, don't draw this. Don't unless you want to. I'm not controlling you. You draw what you want. But so let's say you're out in space and you're doing a spacewalk and you happen to have what looks like a large yoga ball, but it's actually filled with lead, entirely filled with lead, and you've got it right there. And your friend who's also in a spacewalk with scoliosis. I'm sorry, I really didn't mean to make your friend have such a curved spine. So your friend is there, and you want to throw the lead ball to your friend, and everybody's motionless. So you throw it, and what happens?
You're gonna fly
This is
backwards.
worse.
You will fly backward really, fairly fast, and the ball is not going to move much because it has a whole lot more inertia than you do. But if you're in outer space, which of these three things weighs the most? Person A, person B, or the lead ball? None of those, because there's no gravity in space. So inertia is a property of massive things, whether there's weight or not. Whether you're in a weightless environment or you're not, if you try to push this, it's going to resist movement more than you resist movement. So you're going to get pushed back more than it gets pushed forward. The basic unit of force is something outside of physics, I don't know if you'll ever use it again, but it's the Newton. And the symbol is just a capital N, or the abbreviation is a capital N. Have we been over why some things are capitalized and some aren't? So why is, sometimes you have a lowercase letter and sometimes an uppercase, but here it's an N, an uppercase. Why? It's a proper noun. It was named after Sir Isaac Newton. So all of them that are named after people are capitals.
Why is it Sir?
The Queen, I don't know if it was the Queen or the King or some monarchical character knighted him. Yes. Lily Wong?
Why is it 0.225?
Oh, well, that's a very long story. Why is it that many? So the Newton.
Wait, also, why is it the same as the meter thing? As the
It's
Wait.
not. It's close.
2.24?
So
2.24?
2.24. Yeah. That's just kind of a coincidence. There are 2.24 miles per hour for every 1 meter per second. But so this is just a coincidence. So Lily Wong, there's no good connection between them. That's why it's a weird number. It's not like somebody chose this weird number. The newtons come from the acceleration of gravity, which just happens to be what it is, and it's measured in metric units. And the metric units are based on a cubic decimeter of water, which is also a liter of water. And French people a long time ago just decided we need to start somewhere. So they started with a block of water that was 10 centimeters by 10 centimeters by 10 centimeters and sort of based the metric system on
How
that.
did they get a block of water 10 centimeters by?
It was a block, and then they said if it were water, then this is how much mass it would have, and this is the weight it would have, and this is, yeah. So
But wait, what kind of water did they use?
right, they used what at the time they didn't really know that water's density varied like it does. They used fresh water at about 4 degrees Celsius, which is about 1 gram per cubic centimeter. And it was all kind of based on that. And then they realized that water's density changes. But this is just two different systems of measurement that are kind of incompatible. Okay, moving on. But if you want to visualize this, I used to tell people to imagine a raw burger patty. So,
Why can't it be cooked?
because if it's cooked, it dries out a little bit. Most raw burger patty, this cooked might actually be better because a burger patty usually is about 1/4 of a pound. This is a little less than that. And if you cook one, then it dries out. So maybe it's not raw. Somebody last class did a little search and they said a banana. They thought a banana, the other class agreed across the board that they would rather visualize a banana
Wait, I
as
can bring in like
for a Newton.
That's a
the
big
quarter
banana.
pounder patty from
And then
McDonald's. We can make it
another
4 pounds.
another thing, this is the best. 1/10 of a Nalgene of water. So just somebody hold up that bottle right there. So if you fill that with water, that's about a kilogram of water because it's 1,000 milliliters. So it's a liter of water. It's a kilogram of water because French people planned it that way, but that would be 9.8 newtons. So if you add on the plastic, maybe it's about 10 newtons. So a tenth of that would be about a newton. And if you just forget what a newton is, you can always look it up. But this is the one that sticks with me. It's about like a quarter of a pound. How many fig newtons is it? I don't know. That you can find that out. So Newton's second law. The first law is the law of inertia. The second law is just a formula, and it is net force equals. Does anybody know this? You know this. F equals ma. Yeah, F equals ma. And the units that we're going to be using for this to make sure that you get the right answers, use newtons for force, and mass we're going to use, well, we'll get to that in just a second. I'm going to write mass in kilograms. This is force in newtons, and then acceleration is just going to be meters per second squared. So that is Newton's second law. But the most important thing about Newton's second law is its net force. So if you say there's gravity pulling on my mouse right now, that's a force. If I plug in the mouse's mass, I should be able to calculate its acceleration. So, but it's not accelerating. The reason it's not accelerating is because there are two forces acting on it. There's gravity pushing down and there's the desk pushing up, and that gives me zero net force. So that's why it has zero acceleration, even though it's got some mass. Definition of mass, there are a lot of different definitions. When I teach earth science, I say it's the amount of stuff in an object. But here I'm going to call it a measure of inertia. So the more inertia something has, the more mass it has. If you've got 10 kilograms of mass, you're going to have more inertia than something that has less. You could also think of it as the amount of stuff in an object. The unit we're going to use for mass is kilograms, which is abbreviated kg. We may use grams sometimes, but you'll just have to convert. And for years and years, I used to tell people, for a kilogram, picture a brick. And I looked up a brick recently, and supposedly a brick is about 3 pounds. So a kilogram is 2.2 pounds, so I was pretty far off. And I was telling the other class, I think it might have been because back when I first started teaching, there was a lot of Mexico drug running going on, and they were always talking about kilos of cocaine, and I was picturing these bricks of cocaine. And I think that's where I got it in my head. A brick is a kilo, but the best way to visualize a kilogram is a full water bottle. Yeah, so maybe I'll get some comments on my YouTube channel.
Is this being streamed?
Yeah, this is being streamed.
Wait, what? I want admin to see it.
I don't care. They can see it. They may know.
Great class.
They may know more about this than I do. All right. They may. Who knows? I don't know what they've been up to. So, on Earth, I know very little other than what I've read on the news. So, on Earth, 1 kilogram of mass weighs about 9.8 newtons. So, 1 kilogram, that's the full water bottle. 9.8 newtons, 2.2 pounds. I'm never going to ask you to convert any of this, but just there it is. Weight. I used to just say weight was the force of gravity. Force of gravity on an object. But I don't think that's really a good full definition, because if we wanted to calculate the force of any of you on any other people in here, we'll do it. Later on in this, 2 units from now, we're going to do Newton's law of gravitation. And if you have two people and you find their centers of mass, let's say that's the center of mass of that person and the center of mass of this person, and you measure the distance between them, you can calculate the force of gravity of this person pulling that person and that person pulling this person. So we're all exerting gravitational pull on one another, but I wouldn't call that weight. You have to really have usually a planet. So I'm going to put in parentheses, usually exerted by a planet or a big asteroid or something like that.
Well, actually, wouldn't it kind of be weight? But it would be so small it would measure it?
Maybe, but I don't know. I don't think you would ever, if you're out in, if these people were floating in space, you're playing this little game, you wouldn't say, oh, I feel heavy today. I mean, you just wouldn't even feel any weight. And if this person were the size of a planet, you could stand on them and then you'd feel weight. But I don't know. But then they'd form into a sphere also. Gravitational collapse. So weight, here's the formula for weight. Weight is mg. So that's how you calculate something's weight. And this is really just an application of F equals ma. So Newton's second law says the net force on something is equal to its mass times acceleration. So if you imagine a ball free falling down from the sky, the only force acting on it is its weight. And if we want to calculate what that weight is, we need the mass of the ball, and we need to know what its acceleration is. So in this case, what is the acceleration of this ball? How fast? It would be 9.8. Acceleration equals negative 9.8. So I could calculate the force on this ball by multiplying its mass times negative 9.8. And that's what's happening here. You calculate weight by multiplying mass times 9.8. Although g can be different on different planets. If you go to a bigger planet, you're going to have a faster acceleration. This isn't negative. This is a positive number because we'll have an arrow showing that weight is downward. So I would calculate this as, like if this is 1 kilogram, this would be 1 kilogram times 9.8, so it would be 9.8 newtons. And then I would say 9.8 newtons downward. And if I put it in a formula, I would say it's negative 9.8 in an equation. That's how weight works. Now the problem-solving strategy. I'll be doing this a lot, over and over and over. And yeah, over and over and over. So first step, when you get to problems like, when we get to number 2 here, or number 3 here, or number 6, which I'll do as an number 7, which I'll do as an example. Just about all of these problems on this page 5 of the packet. You should do these steps. So the first step is to write. You don't have to write the word write, but I'm going to write the word write. Write net force. So if you want to find, say, the acceleration of an object, or the force on an object, or whatever else, you write an equation for net force acting on that object in terms of the individual forces acting on that object. So you write net force equals the vector sum of the forces acting on the object. And over here on the side, I'll just give a little example, but don't really have to do that. This is the quintessential situation where we'll do this. So for example, you've got an elevator. There will be a ton of elevators. And this elevator, the weight is pulling the elevator down. Weight we can calculate as mass times g. And then there's the tension in the string pulling the elevator up, which is, well, we could write that as T for tension. So the vector sum here means I add these forces up. Would T be positive or negative in my picture? Positive, and mg would be negative. So I would just write net force on this elevator is T minus mg. That's how I would do this first step. And then I'd do the same thing. I'm going to write another formula for net force, or another equation for net force, but I'm going to use Newton's second law. No, you don't. You don't. I'm just doing that because there's going to be some point where somebody is going to list some forces in here that are actually acting on the string. And they're going to add them in, and they're going to get wrong answers because they're not really remembering, oh, it's just the, or actually it's, there's one where we'll have a person in an elevator standing on a scale. And the important thing there is the force is acting on the person, not the scale, not the elevator, not the string. You've just got to really focus on what object you're talking about. In this case, I'm talking about this box. Its weight pulling it down and then the string pulling it up. Bless you. So I'm just, these are the mass of the object and the acceleration of the object. And then finally, guess what I do? Once I get net force of the object equals this, and net force of the object equals that, guess what comes next? I've got two equations for the same thing.
Systems of equations?
Yeah, set them equal to one another. So I substitute, or whatever you call it, I don't know, system of equation. I'm just going to say substitute because I can't, I feel like there are too many T's in here. Substitute, and I'll just say the vector sum equals MA. And then really the unwritten step 4 is to solve. But it's going to be that over and over and over again. And then we get into 2 dimensions, we'll be doing that in 2 dimensions over and over again. So a few little practice problems. Number 1, we don't need to do this. It's just so simple. This is just using Newton's second law. If you've got a 91 Newton net force applied to an object, and the object accelerates at 8 meters per second squared, what's the object's mass? So this is just an application of net force equals ma. Given the net force, 91 newtons, the mass is what I'm looking for. The acceleration is 8 meters per second squared. So divide both sides by 8. And the mass is going to be 91 over 8, which is 11.4. What would the units be for mass? Kilograms. And somebody pointed this out earlier. If you look at the way units work out, mass is kilograms, and acceleration is meters per second squared. And if you multiply them together, you get kilograms meters per second squared. And that's another name for a Newton. A Newton is a kilogram meter per second squared. Now, number 2, get to use the strategy here, although this is a really easy one you could probably do without it. 1,200 kilogram car. Here's the car. And there are step 0, draw a picture showing all the forces. On the object. Yeah. I guess I was just assuming you would do that, but I should write it down. So there's a 1,200 kilogram car being acted on by 2 forces. The motor is providing a 1,000 Newton rightward force. And friction is providing a 300 Newton leftward force. What's the car's acceleration? Now, I've left out the weight of the car and the normal force. I'm not including those in here, but they would cancel out anyway. This car is not accelerating upward or downward, so I can leave them out. So my first step, I'm going to add up all the forces acting on the car. So the net force on the car, I could write car there, but I won't. I'll just do, would it be 300 minus 1,000 or 1,000 minus 300? 1,000 minus 300. Because 1,000's to the right, 300 is to the left. So that's the net force. And I could go ahead and solve and put 700, but I'm not going to write that yet. And then the other way to find net force is to do mass times acceleration. And in this case, the mass is 1,200. And the acceleration is, I don't know, that's what I'm looking for. So this is the net force, this is the net force. I can set them equal. 1,000 minus 300 equals 1,200 times A. So 700 newtons equals 1,200 kilograms times A. So A is just 7/12, which is 0.58 meters per second squared.
Wait, you need to do the like set them equal to each other step, or could you have just written 700 equals 1200?
That's still setting them equal.
Yeah, but he did that whole like other step.
Yeah, I was just showing my work.
Okay.
Yeah, I'm doing more than I would do if it were just me in private.
Okay.
So, bowling ball is sitting motionless on the ground. Here we go. There's the bowling ball. The ground is applying a 49 Newton upward force to the bowling ball. What's the bowling ball's mass? I'm going to draw this. This is the force of the bowling ball. Or sorry, the force that the ground is exerting on the bowling ball. Are there any other forces acting on the bowling ball? The bowling ball is like my mouse.
Isn't it like the normal force?
So that is the normal force. Yeah, 49 newtons would equal the normal force. That's the force by this surface exerted perpendicular to the ball.
Wait.
The other one is the weight. Yeah, there's weight pushing this way. And I guess if I wanted to, I could write it equals mg, because I know that weight equals mg. So there's a good full diagram. I'm looking for mass, and I can find that from this, I guess. So the first step is to, and this is kind of so easy. Some of you can just, in your heads, you're probably already there with what to do. But I'm just going to do my process because it's good practice. So I'm going to add up all the forces here. This is one force, and it's upward, so it's positive. And then this force, which I could either call weight or just go ahead and jump in and call it mg, because that's the formula for weight. I'll do that. So I'm going to do 49 newtons minus mg. And that's one way to, this is the sum of all the forces. The other way to get net force is to do mass times acceleration. I don't know the mass. I'm looking for that. And what's the acceleration of this ball? It's motionless. The acceleration is 0. So this is the net force, and so is this. So I can set them equal. So mass times 0, I'm just going to write 0 equals 49 newtons minus m. And at this point, I'll go ahead and put in g times 9.8 meters per second squared. So let me add negative 9.8 m to both sides. Or sorry, add positive that. So I get that, and then I can solve for m. The mass is 49 newtons over 9.8 meters per second squared, which is 5. What will the units for mass be? Kilograms. So those are 2 examples. These are kind of easy ones. And yeah, Emmy?
Like, not really a good question, but anyway, did
It's
you
okay.
do that in your head? Did you do the 49 over 9.8, like, just now? That sounds good.
You see that a lot. And I did it last class, so I remembered it. But thank you. Yeah, you'll see 49 a lot. You'll see 39.6 a lot. You'll see 19.6 a lot. All these are just multiples of 9.8 that crop up again and again in these problems. 58, you'll see that one a lot. Okay, so let me go over the homework. Number 1, right here, conceptual questions. That's part of your homework. Number 2 is part of your homework. Don't do number 3. We're not ready for that yet. We haven't gotten to Newton's third law. Then for problems, it's going to be 1, 2, 3, 4, 5, and 6. But I want to do 7 as an example. So you can cram this in there if you want. I'm going to write it on a separate sheet of paper just so you can see what I'm doing more clearly. If I were you, I would just kind of squeeze it in there. There should be plenty of space, but if you may want to get your own paper too. I won't deny you that. So this is a hard one, and if it seems confusing the first time, that's okay. We'll just be doing a lot of practice with these problems until they start to become second nature. So there's an elevator. We're given the mass. It's designed so that the maximum acceleration is 0.068 g. What are the maximum and minimum forces the motor should exert on the supporting cable? I'll draw my picture. Here's the supporting cable. What I didn't really understand about this problem when I first read it is this acceleration could be upward acceleration or it could be downward acceleration. So at times the elevator is going to accelerate upward this fast, and at times it's going to accelerate downward that fast. So when do you think this cable would have more force on it? Imagine I pinch right here and I pull, lift it up with that acceleration, or I hold and I lower it down with that acceleration. When do you think I would be putting more force on the cable? Pulling it up?
Would it be like right where you're standing?
Yeah, well, you mean when I like,
You could just free fall.
yeah, so if you did that, if you were holding the cable and you just let go, how much force would be on the string then? Very little. So given that fact, given the fact that there's no force on the cable at all when you let go and they fall really fast, when do you think you're going to be applying more force? When you lift them or when you let them go?
But how about like when you are lifting up after it's been falling down? 'Cause we could be
Ah, so it's a, yeah, but well, that would still be the same acceleration. So if you had the elevator accelerating downward at this rate, and then you start to accelerate it upward, it's not going to move upward right away. It's going to slow down going down. So I think it would be, I don't think that would really matter as long as it's either upward or downward acceleration. But back to the fish thing, just imagine you've got a fish. This is the fish. You're holding the string. Are you more likely to break the line if you yank the fish up or if you lower it down? Yank it up. So just setting the stage, we're going to find the maximum acceleration, or sorry, the maximum force when the acceleration's upward. But I'm going to do my steps now. My steps are net force equals, and I want to add up all the different forces acting on this, just the elevator, just this, not the cable, just this part. So what's one force acting on it? We've got an elevator here. Tell me, what's something that's pushing or pulling on the elevator? Cable. Which way is it pushing or pulling? Up. And that, I'm just going to call that tension. That's what we usually call the force in a cable or a string. What's the other force? Weight going down. And I might as well write mg next to it. So those are the two forces. That's it. There's no other force acting on this. So if I write the sum of the forces, it's just going to be, this is positive because it's up. This is negative because it's down. So it's T minus mg. So that's the first step. Write out the sum of the forces. And then the second is to write net force, but use Newton's second law, which tells us that the mass of the elevator times its acceleration is the net force. So this is the net force, so is that. So now I set them equal. I'm going to write it like this time. I'm going to say T minus mg equals ma. And there are some nice little things like, you could start plugging things in at this point, and you could solve, but I kind of like to do some algebra stuff. Can anybody think of a way to neaten this up algebraically? Tidy it a bit? By mass? What? Yeah, but I can't really do that yet because this doesn't have mass. Yeah, I'm going to add mg to both sides. So I get T equals mg plus ma. And now I can factor out that mass. So I can say T equals m times g plus a. You don't have to do this, but it just gives you a simpler thing to work with in the end. So now I can start plugging some stuff in. The tension, that's actually what I'm looking for. I want to find this. That's going to give me the motor force. The motor is what's causing this tension that's lifting or letting this thing down. And the mass I was given, 4,850 kilograms. G, I know, is 9.8 meters per second squared. And the acceleration is 0.068 g. I can't really add that to meters per second squared. Let me just write it over here, and then somebody tell me what to do with it. What do I do with this? It's got different units. How could I get the units to be meters per second squared?
Multiply it by 9.8.
Right, so this is 0.068 times 9.8, because 9.8 meters per second squared is G. And I'm looking, Emmy, at my answer key from the other class. I'm just cheating here. Except, oh, I wrote it somewhere else. Dang. Is it over here? Oh, here it is. 0.67. I just rounded. 0.67 meters per second squared. So that is actually the acceleration. And what do we want to do first? Do we want the acceleration to be up, or do we want the acceleration to go down? Do you care? Let's make it upward right now. So if the acceleration is upward, is this going to be positive 0.67 or negative 0.67? Positive. So I'm just going to leave 0.67 meters per second squared. When I add those two together, I did this all at once last class. I think I got, well, what is it, 10.47, and then multiplied by 4850, and I got the tension of 50,800 newtons. So that's the tension in this string when you have positive acceleration. So I'm going to say upward acceleration just to keep track of what's going on here. Now if I do use my same formula again, but I'm going to put in negative 0.67, then I get, let me do downward. Just making a little note here. So I have T equals the mass of the whole thing, 4850, times G plus A. So in this case, it's going to be minus 0.67 because the acceleration is downward. And that's going to give me a smaller number. T is 44,300 newtons. So this would be the minimum, and this is the maximum. And tell me if intuitively this makes sense to you. The tension looks a lot like mg. Mg is what weight is. Here's the mass, here's the normal acceleration of gravity. If I just wanted to find the weight of the elevator, I'd multiply 4850 times 9.8. But when I'm yanking it upward, I'm not multiplying it by 9.8, I'm multiplying it by 9.8 plus a little bit. So this is sort of like a simulated gravity that's higher than usual. And when the thing's being lowered, I'm multiplying the mass times not the normal gravitational rate, but a little less than that. Does that make sense? It's just one way of looking at it. So your assignments to do, problems 1 through 6. And I was having a lot of trouble getting this link to work on my website. Right here, this link, it keeps saying not found. So I put this in Google Classroom, all the answers. Sorry, let me go to Google Classroom and show you where the answers are if you want to check everything. Under classwork, class 17 homework solutions. So it's all right here, conceptual questions and then problem solutions right there.